Thank you everybody. So today we're going to be looking at some more application for the Lorentz equations. But no, not the Lorentz equations. That's silly. Today we're going to be looking at the dynamics because we've already covered how relativity is a substitute for kinematics with all that rocket stuff and stuff. Yeah, I don't quite remember what happened in the past 5 lectures. But now, today, we're going to be covering a dynamic. So today we're going to be looking at dynamics and relativity. So if you've been watching our earlier lectures, maybe ones that were in our double digits, then you would have noticed the law of the conservation of momentum. So now, what? Hello? Please? If you suggest, Mr. Rodriguez. So, today we're going to be looking at the conservation of momentum and how it changes in relativity. Well, you usually think of momentum as conserved and absolute. But let's take a deeper look into the equation. If you are a basic physicist, you most likely would know that momentum is equal to mass times velocity. However, let's see what happens when we take a little bit deeper of a look into not mass, not momentum, but velocity itself. Remember velocity. We know that distance is relative and time is also relative, so therefore velocity must be relative. Meaning that if velocity is relative, that means that momentum itself is relative. But this contradicts what we think about in the conservation of momentum. So, is physics broken? Or do we simply need another set of equations? That's what physicists thought when they noticed the conservation of momentum overlapped with the Einsteinian theory of relativity. So, they devised a new set of equations. So, they made it so when you were traveling at high speed, you would add a gamma here. Because gamma shows that when time is dilated or contracted, so is velocity. So, this is the factor that time is dilated by or contracted by. And that shows how velocity is stretched or compressed. So now, with that done with, I want to show you a certain example of what we're doing. Well, say that we take a 20 kilo object, send it flying at a velocity of maybe 84% of c. You'll see why that number helps us later. And then we have this, which is going to be gamma, which can be expanded. So that gamma will be expanded into 1 over the square root of 1 minus v over c squared. Now, from what I believe, that's going to be equal to 1 minus 0.84, which is going to be equal to 1 over square root of 0.16, which is obviously going to be 1 over 0.4 or 25. That gives us a gamma of 25. But now we have to multiply it by the rest of the equation. 20 times 0.84c. Well, this is pretty awkward, but we can make it less awkward. By multiplying this by this, we get 500 times 0.84c, giving us 84c 84c times 1 for 5 is equal to 420c. Now, that's obviously really high. But what happened if we used the original equation on this kind of velocity? Well, it obviously wouldn't work out. We would get different results that aren't representative of the actual answer. See this? Look at this. 20 times 0.84c. That's way smaller than our original answer, and not how it's supposed to be when you're going at such large speeds. So that only gives you a certain amount, like, it's a fifth of 100. So what is 84 fifths? That's going to be equal to, sorry, I'm just doing a bit of math here. That's going to be equal to 16.8. So 16.8c, which is significantly smaller than this beauty that we have conceived right here. Thus, that gives us a certain kind of graph. While when you're looking at the regular equation, it's obviously linear. It's the simplest kind of graph you could ever encounter in your life. When your velocity increases, so that you're in momentum. And the same says with mass. Now, when your mass increases and your velocity stays the same, we go on the same kind of loop because P is set to 1. No, I meant gamma is set to 1. However, something very strange happens when we set it back to V. So if who spilled the bucket? So if I get a different color in here, we can investigate this. Now, this would look seemingly linear at first, but as your velocity approached V, slowly got outrageously high and soon curved to the highest it could be, breaking the charts. So, the limit is reached when you try to get close to when you get as close as you can to the ultimate speed, the speed of light. Well, now I just want to excuse me. Oh, we have a new student.
Hello, Professor.
Thank you for bringing a glass of water for me. Now, we're going to... Now, we just lost one extra student, which is not good. And now, since we don't need this anymore, you know what we do with it. Next up, we get back to the lecture. So now, this is a very strange phenomenon because because of relativity and all this relative stuff, we have to change and twist what we already knew about in classical physics and reinvent it to become new and moderate for what we actually use. One more insight, this actually just reduces to the original equation when you set your velocity to ordinary speeds, which is unfortunate.